we can move on to the temperature. So the temperature is a bit more tricky because temperature affects the reaction in two ways, and that's the really important part about it. The first way that temperature affects it is that temperature affects the reaction rate. So what that means is that temperature is another way of saying we've got a certain amount of energy in the system. And the more energy there is in the system, the more chance there is that any one molecule will hit this activation point that's up here and then proceed to react. But just like a catalyst, if your products are hot as well, if you've heated up the whole system, then there's more chance they'll go back the reverse way as well. So this aspect of temperature, it's not the only aspect of how temperature affects the reaction, but temperature speeds up the reaction rate for both sides in the same way as a catalyst. So that's the first effect. But it's got a very important second effect as well, which we're going to have to balance in this. And that second effect is that, according to Le Chatelier's principle, temperature will force the equilibrium reaction in one direction or the other, depending whether the reaction is exothermic or endothermic. So it'll go in the opposite way to the heat that the reaction itself creates. So if the reaction is exothermic, that is to say that the reaction releases heat, which what this one does when the products are formed, then increasing the temperature will shift the reaction to the left. If it was an endothermic reaction, force it to the right, but this is an exothermic reaction, so increasing the temperature is actually going to force this reaction to the left. Now, that would decrease our yield. So does that mean that we want to cool the whole reaction down because that will force the reaction to the right? Well, it would, but the problem with that is it would also slow the reaction rates of both sides down, so it would act like an anti-catalyst in that respect. Even though it would be increasing our yield on paper, it might take hundreds or even thousands of years to achieve that yield. Whereas if we heat it up, we might decrease our yield once again on paper, but because the reaction rates are high, we'll actually be creating more ammonium in any one moment. Then again, if we heat it up too much, we might force it so far to this side that we decrease our yield again. So there's actually an ideal temperature to do this reaction at, where the rate of reaction is balanced out by the lack of yield, and you get like a sweet temperature to carry it out at. That temperature is around about 350 degrees Celsius. So at that temperature, yes, we are shifting it to the left, but but we're also increasing the reaction rate, and that more than makes up for it until about that temperature. Go above that temperature, and it doesn't make up for it anymore, which is why we only go to that temperature. So that's quite tricky. There's two effects, and they're opposed to each other. But if we can find the right temperature, and in this case it's 350 degrees, we can increase our yield of ammonia. Alright, the next thing is removing a product. Alright, so you might remember this one from esterification. Basically, the whole idea, this is another one of those kind of basic equilibrium things, which is that the whole equilibrium relies on the concentrations of the substances remaining constant. If you remove or add a substance, that changes the equation. And by removing a product and putting it into a state where it can't undergo this backwards reaction, we can change the equilibrium dynamics. And in particular, we can increase our yield. If you're constantly removing this, then it doesn't exist to change back, is the essential factor. Now, the problem with removing a product is that all three of our substances, our two reactants and our one product, are all gases. So it's hard to, you can't just pump out a product or something like that, because they're all mixed together as gases. The way that they get around this is they take advantage of a property in the of the gases, which is that the ammonia will liquefy first. So, whilst on the one hand you've got all of this stuff going on in the reaction chamber, the catalyst going across, so that's the reaction chamber. What we do is we take things out of the reaction chamber. There's still going to be a mix. It's not going to be, so this is going to be N2, H2, and NH3 in different proportions. And then we feed it into some kind of cooling chamber, which is at the right temperature for the NH3 to condense out, and then the nitrogen and the hydrogen continue on, and they get recycled in to the reaction chamber. So by doing this, and then they'll get heated up in here as well again. So this is colder, and this is hotter. Let's discuss, this is 350 degrees. So this is the final thing we can do to increase our yield, which is to just remove the product so it stops going back into nitrogen and hydrogen. When it's cool in a liquid form, it won't do that very quickly anymore. And then we recycle in the nitrogen and hydrogen to undergo the reaction again. Alright, so that's the 4 tricks that we use for the Haber Bosch process. We use a catalyst, we increase the pressure, we increase temperature the right amount, not too much, to what we call a compromised temperature, and we remove the product. So that's the central core of the Haber Bosch process. There's just a little bit more that you need to know about it. So we've done the kind of the back end. This is the back end of the Haber Bosch process. The main reaction over here, and removing the nitrogen by cooling it, liquefying it. Sorry, removing the ammonia. Removing the ammonia by cooling, liquefying it as it forms. Now the only extra thing you need to know about is the input product. So when we talked about the core process, we needed nitrogen and hydrogen gas, and we just fed those straight into chamber and everything. So the question is, how do we get these? Alright, nitrogen gas. We can fractionally distill air just like we fractionally distill oil, same kind of concept, except we use colder and colder platforms that we run the air past, and then different components of air liquefy out and run out. So this is a very cold chamber, and one of those fractional components of air is nitrogen. Nitrogen is of course like something like 73% or a very high percentage of the air that we breathe. So simple as that, no chemical reaction involved, it's just a fractional distillation process. Hydrogen, bit more tricky, not too much to it though. With hydrogen, we have a source, we have a pretty good source that we can get hydrogen from, and that source is CH4, methane gas from fossil fuels. Now, as you might remember, hopefully you will remember, methane gas is carbon, 4 hydrogens around it. And it's not too difficult to separate these H's out and get hydrogen gas. What we have to do is react it with water at a very high process, at a very high temperature, and with a catalyst. So it's just this reaction here. It's methane plus 2H2O goes to, it's actually equilibrium, 4H2 plus 2. Now, there's actually a multi-step process involved in this conversion, but this is just the reaction that you need to know for the HSC. So methane plus water goes to hydrogen gas, which is what we wanted, and some carbon dioxide that we need to get rid of before we send the hydrogen into the reaction chamber. They get rid of the carbon dioxide just by using a compressor, and that's catalyzed by nickel oxide. Okay, great. So that is the Haber Bosch process in a nutshell.